Hi everybody, in this YouTube video I would like to discuss the difference between the Ito versus the Stratanovich calculus. So this is in the general framework of stochastic processes, and what's the consequence for the interpretation of the drift and diffusion tensor. And this is highly relevant when you have to analyze single particle trajectory data. So I would like to start with the following motivation: is what is the difference between a Brownian motion or a diffusion that occur in three different medium. So suppose we have here water, here we have, let's say, oil, and here we have honey. So suppose you have a Brownian particle that is moving, and for some reason the particles go into this layer, move into the oil, and what's the intuition is that in the oil the particle will have a smaller diffusion coefficient, and it's even going to be even more when it goes through this honey layer. So suppose we have a stochastic processes that can be described by a general equation such as x dot equal b of x, the drift plus the diffusion coefficient or diffusion tensor. So obviously if the medium or the three mediums are homogeneous, we have a description here by a first diffusion coefficient, a second one, and a third one. And let me remind you the classical theory, which is the diffusion coefficient equals the Boltzmann constant, the temperature T, divided by mass multiplied by gamma, which is the friction coefficient. So gamma is friction, and in general we have the expression that it depends on the size of, let's suppose we have a ball that is diffusing of radius a, so this is 6 pi a and eta, where eta is the viscosity. So what do we have here? So we have basically three different viscous fluids. So we have three different diffusion coefficients. And where are basically the changes that occurs is specifically at the interface. So we have here two interfaces, one here between water and oil, and the second one between oil and honey. So we expect, if there are to be change in the behavior, that in a small layer between these two interfaces here, we expect a different behavior than classical diffusion would predict, such as, for example, maybe local accumulation here of particles in a very narrow boundary layer. So in practice, how to simulate this situation? So what is the simulations? So in terms of simulation, what we are expecting is that we can use the classical relation of the Euler equation, which said that xt plus delta t equals x of t plus square root of 2d square root of 2d delta t, right? So this is okay as long as we are staying in and multiply here by a random variable. So this is okay as long as the particle stays inside one of these three regions. Let's call it Ri. Okay, for I equals 1, 2, or 3. But so what happened at the interface? So if we are at the interface, we may imagine that the process, since we are having here switching So you start at particle at position 1, and it switches to particle to position 2 and 3 and so forth. And so the computer is putting the line. So if we are here at time t, and at time t plus delta t we cross the region, obviously if we use this equation we are probably making a mistake, because we are using the same diffusion coefficient. Let's say if we start from region 1 and we arrive to region 2, although in region 2 this approximation by d is incorrect. So this probably suggests that we should change the way we do the simulation at the interface, probably saying that x of t plus delta t, we should probably imagine that we have a first point of intersection, and so from xc we change then the position of the last point with 2d2 something like delta t 1 minus alpha, where let's say we have alpha which represent the fraction of the trajectories. So alpha is, let's say, xc minus x divided by the total length here of the trajectory, which is xt plus delta t minus xt, and so L is xt plus delta t minus xt. Right? So this shows that the interface, we need to correct the classical scheme. So I'm not going to go more into this direction. I would just want to refer to what we wrote a couple of years ago with Zinger and Schutz and so on. This was published in the journal of the Siam Journal of Applied Math in 2008, where we did the local analysis of this boundary layer. Okay, so now I would like to show you another example about in what condition the diffusion coefficient can change. And this is the following situation. So let's call this second example, example 2, in what condition the diffusion coefficient can change. So suppose you have an ensemble of obstacles, and these obstacles are changing in size and in density, right? And so what you imagine is that you can have a diffusion process that is moving inside this structure. And of course, as the particle goes into a region where you have a higher density, the particle can have a restricted motion. So let me add here 2 more of this structure, where you can see what can happen is that the particle can really be trapped here and eventually escape in one of these 4 different places. So what do we learn from this? So we learn that there are here obviously 2 scales, right? So there are 2 scales. One is the scale which is basically given by the diffusion process. So one is given by the diffusion d, and it's it can be related. Let's say if we give a certain length, we can estimate from this a time, and I'll come back to this in a second. And there is a second one, which is an effective diffusion coefficient, which is given by calculating the time it takes to escape from this region. Let's call it omega. And this probably could lead to an effective diffusion coefficient. Effective diffusion coefficient, let's call it dE, right? And so dE is, for example, the effective is given by the, let's say, the size here of this square, let's call it A squared, divided by the time it takes, or 1 over the time it takes lambda to escape, divided by 4, where lambda is 1 over the time to escape. This is the time to escape here, this domain through this little hole here that I'm marking in green. All right, so this shows that there are here 2 diffusion type of behavior, and if we fix a scale, a time scale delta t at which we're observing the process, I would say that if we have a time scale which is much less than the time of escape, then basically the process can be described by the diffusion coefficient d. However, if the time step delta t is bigger or much bigger than this time to escape, then this process has to be studied using the effective diffusion coefficient. And this is well understood if we look at the graph that is done usually classically. We calculate either for empirical data or on a simulation, we calculate the mean square displacement of a trajectory generated by simulations. So you have dx squared as a function of delta t. So what we should get here is basically two behavior. One at small time, d small, which is the d effective. And the second one, the second line, is at d. So if we are at small time scale delta t, the trajectories will be going through this line. While at long time scale, we expect things to be collected and arriving here, this dE. And in between, we have to glue continuously the behavior. So then we should expect a sort of diffusion coefficient that will vary. And that's the reason I wanted to show you this example, is to explain how the diffusion coefficient can vary as a function of the position and the time resolution delta t. And so this is important to understand how to use stochastic processes in such analysis. So now I would like to recall the definition of the Ito versus Tretanovich calculus. So in one case, it says basically that to integrate a function with respect to the Brownian motion S, you have to use a discretization. And the discretization is you can either use a point when you discretize a time ti, and then you make the difference omega of ti plus 1 minus omega ti. And this is the classical Ito for the functions that are non-anticipating, that is, they are independent of the future. But there are also many possibilities, and an extreme one is to use here f of ti plus 1 plus f of ti. So this is a classical Riemann's integral divided by 2. And then I have to multiply by the same thing, omega ti plus 1 minus omega ti. And so the question, so this is called the Ito form. This is called Ito, and this is the second one is called Stratanovich. And the question is, if we go to the limit, so this sign is actually, we have here to go to some limit as the time delta t goes to 0. In the limit, we'll see that there are differences in these two considerations, these two forms. And the question is, what's the relation between the Ito forms and the Stratanovich form? So if we have a function and we just apply what we have f d omega s, and we just use the discretization and we write it the way it is written above, omega of ti plus omega of ti plus 1 divided by 2, and then we multiply by d omega, and I would like from this to obtain the Ito form. So I'm going to use a Taylor expansion by expanding f at the middle point with f at the point omega ti only. So this is the sum of f of omega ti plus the first order term, which is a derivative. So I have to first to use omega ti plus 1 minus plus omega ti divided by 2 minus omega ti. So this is just omega ti divided by 2, right? And then I have to multiply this by another d omega and the derivative of f of omega ti, and the plus of the term that I do not care. So if we go to the limit, what we are left with, so here there is d omega, is the integral of f, but in the Ito sense. So let me write it d Ito omega. And in the limit here, where you have to consider the limit of the omega d omega square when delta t goes to 0, it converges to the delta t term, which is 1/2, because d omega squared, the expectation of this is dt, and we can show that the limit converges to the expectation. It's 1/2 dt f prime dt. And so we can write it now in the form f d Stratanovich is equal to f di of Ito plus 1/2 of f prime dt. Right? So this shows the first interesting formula to connect in terms of the differential form for any function f. It showed the relationship between these two representations. So the next thing what we would like to study now is what happened for the representation of a stochastic equation. If I have an equation for the Ito form, which is dsx equals b delta t plus sigma d Stratanovich of omega, and we would like to see the connection for any function f with the Ito calculus. So for this, I write d, or this little delta, capital delta of d is the same, Stratanovich of any function that depends on x. So again, this is, so I'm going to use the Taylor expansion. This is df, and this is df dx at xi plus 1 divided by 2, and then I need to take this x ds of x, which is b of xi plus 1 divided by 2 delta t plus sigma of the same x. I'm not going to write it because it's will hit all the space, so xi plus 1 divided by 2 d omega. And then I need to go to the second, although I'm not going to use it, second order term, ddf ddx square, and I have here just sigma square delta t. So I'm interested only in the first part, so I'm not going to carry much this term, but you have to keep it in mind. So similarly as what we did before, I will express everything using a Taylor expansion with respect to xi. So what you'll get is df dx at a point xi multiplied by bxi delta t plus, and then you have to use the first derivative. This is ddx of ddf of f multiplied by b multiply by delta t. And then I need to continue the expansion, which is plus. Yeah, so let me go back. So this first term is okay. This is it's also okay. I have to multiply ddf by dx. Let me carry the next term. Plus df sigma dxi d omega sigma plus d omega 1/2. This the first term is. Yes, this is correct. 1/2. And then I need to multiply by ddf. ddx df of sigma df dx multiply by d omega delta t dx plus the term of order 2, which I'm not writing, of order 2. Okay, so next, if I continue this is equal to, so I'm neglecting the term of order 2, so we are left with ddf dx multiplied by b delta t. The term of order 2 I don't care, so I'm left with plus ddf dx sigma d omega plus 1/2 of sigma ddx of sigma df dx multiplied by d omega squared, and plus the term of order 2. And so in the limit here, where we go to the stochastic integral and take the limit when we discretize the domain and so on, as we did many times before, we get that d Stratanovich of f is d dx b plus 1/2 of ddf dx squared sigma squared plus 1/2 of sigma ddx sigma ddf dx delta t plus df dx sigma d omega. Okay, so this is coming from the second order term. This is the first one coming from here. We have the new term coming from there. And so what happens if I take f equals the identity matrix, or the identity function, that is f of x equals x, and I apply this to this equation, basically I get this Tretanovich of the process x. df dx is identity, so I get b, and here I'm missing I'm missing here delta t, and yes, multiply by delta t, and so I get plus second derivative is 0. I get one term which is 1/2 sigma ddx sigma, so everything is dt, plus I got sigma d omega, which is the Ito case. Alright, so this shows the novelty that we have win here. This is this drift term, and so this is important because it says it represents basically the contribution if we have a diffusion tensor that is not constant. And we have seen in previous examples what could be the consideration to have a sigma which is not constant. It in physical space, it corresponds either to a change in the density or a brusque change in the viscosity, right? And so there is a general question of interpretation of what is the meaning of having a sigma that is not constant. So I can give as an exercise the following question is, suppose we have an ensemble of ball, and suppose the distance here between the two is dependent on the position. We call this distance Lk. And for example, Lk can decrease. And we start with a stochastic process, x dot equals a of x plus square root of 2d w dot in dimension 2. And so you have, suppose the process is independent of the heights. So what is the effective diffusion process when we reduce this to a Markov chain where the particle is actually escaping, and now everything is coarse to points. So this is point xk, xk plus 1. So this point does not exist. It is here xk plus 2 and so on. I would like to reduce these processes where you have particles moving here in between the obstacles into a process where particle can switch between what is called the center of these domains. This is an elementary domains. Okay, so as an exercise, what is interesting to show is that if a of x is 0, if this is 0, then the process associated to this 1D, so this is the 1D reduction, this 1D reduction is actually a process where there is a drift, and the drift A, that depends on k, can be written as Lk divided by 2 times k right. So this is a time to escape in the right here when you are at k, and this is left, right and left, minus Lk minus 1 divided by 2k left, while the diffusion coefficient is simply 1/2 of Lk squared divided by 2 times k right plus Lk minus 1 squared divided by 2 times k left. Okay, so this shows that although there is no drift in the initial process, you have an effective drift in the reduction. And so to conclude, let's make the final slide about the conclusion. I would say that in general, the Smoluchowski equation, the Smoluchowski limit of the Langevin equation, has been derived in the case where d is constant. And so this is the framework to derive the Langevin equation and the Smoluchowski limit. So any deviation from this, we need to consider what happened at a molecular level. So there is no general theory about how to calculate the diffusion coefficient from this molecular consideration. So any analysis requires to go back to the molecular level, requires to study the molecular level. We should not start with assuming the diffusion coefficient has such a value or such value, because it makes no sense. We have seen that if you have to go through region 1 and region 2 with two different viscosity, you are going to see a major difference at the layer, at the boundary layer, which should be studied separately. If you are interested in what happened when you have obstacles at different, with different density, what needs to be studied is the resolution. What's the resolution? The time scale delta t. We should start with Ito as it is non-anticipating, except in the case of when you have a full signal and you go back in time, and this is usually used in signal processing. But in general, we have a given resolution, and we should study what is d at this resolution delta t, which is different in different data sets, because you sample the trajectory at a given resolution. And so if you go to a smaller delta t, you sample the space differently, which leads to a different resolution of your sample. Okay, so in general, my opinion is that do not start at the macroscopic level, start at the microscopic level, and the diffusion coefficient should be calculated the way we show it in here at a given resolution, and the drift term that can be estimated starting from the Ito calculus. Of course, when the diffusion coefficient is constant, there is no difference between Ito and Stratanovich for the drift term, although I show it to you here that if we coarse graining, which is a different process, it's a different approach, different modeling, you end up having a drift. Okay, I hope it helps for this understanding of Stratanovich versus Ito. Thanks.